Sorry, we are waiting for the bus to come. Actually, the bus has arrived. So they are taking some time to cross check. For the security reasons, there's some delay at the main gate. But the participants from Delhi should be here soon. And once they're here, we will start the talk. Please wait. They are at the main gate. Samosas are all gone. Hello. Welcome, everybody. First of all, I'd like to thank you all for attending today's event. It's a very special event for us. As you know, that the physics department of Ashoka University is a comparatively very new department. We started our journey in 2017, and now we are thriving with very brilliant, our UG students and PhD students. And they are very active. They have Physics Society, Astronomy Society. You must be receiving their emails all the time. And we are also happy that being such a new department, we got this opportunity to host this very prestigious event. And I definitely thank Professor Anjan Anand Sen, the Secretary of IAGRG, who has given us this opportunity to hold this event here. And first of all, I'd like to invite Professor Anjan Anand Sen on dais to say a few words about IAGRG and the award which has been awarded to Professor Varun Sahni this year. Anjanda.
Thank you, Shuratna. So, good evening all. And on behalf of IAGRG, I welcome you all to this Vaidya-Raychaudhuri Endowment Award lecture. Just a few words about this IAGRG, the Indian Association for General Relativity and Gravitation. It was started its journey in 1969 and was started with the stalwart of Indian relativity community like Professor V.V. Narlikar, Professor P.C. Vaidya, Professor A.R. Raychaudhuri. And now we have, its main aim is to promote research and activities in the areas of general relativity and associated fields in universities, research institute, colleges. Currently, we have around 400 members among universities, research institute, mostly in India and also from abroad. We have, I mean, every year we have different programs under this IAGRG. Like we have this IAGRG National Workshop every 2 years. We have this ICGC, which is the international workshop. It happens every 4 years, and the next one will be happening in December 6 to 9 in IIT Guwahati. Just recently, we have started for last 2 years a training program like IAGRG Summer School on Gravitation and Cosmology. Just this year, this summer school just concluded at ICTS Bangalore, and the next summer school will be next school will be around October 2024. It is already been funded by ICTS. On top of that, we have few awards that we have every year under IAGRG. One is the N.R. Sen Young Research Award. One is V.V. Narlikar Best Thesis Award for the PhD thesis. And the most prestigious is the Vaidya-Raychaudhuri Endowment Lecture Award. Every year we have. And on behalf of IAGRG, we are honored to present this award to one of the outstanding relativists and cosmologists from India, Professor Varun Sahni from IUCAA. And I congratulate Varun for this. I mean, on behalf of IAGRG, we are really thankful to Professor Raychaudhuri and the colleagues in the physics department, Shuratna, to organize this prestigious event in Ashoka University. And thank you very much. So I give.
Thank you, Anjanda. I now invite our Honorable Vice Chancellor, Professor Somok Raychaudhuri, to come here and introduce our distinguished speaker.
Thank you very much. Thanks, Shraddha. And thank you so much, everybody, for coming today. I mean, it's almost a rock star event. That's fantastic. And he's a rock star himself. I mean, I would use the word swashbuckling astrophysicist. It's an honor to introduce Professor Varun Sahni, one of the absolutely top cosmologist and astrophysicist of the world. I've known him for more than 35 years. And so I'm not just introducing him as a guest here, but also as a very close friend. Professor Varun Sahni did his, I mean, in cosmology, there were two big schools during the Cold War that developed the subject from general relativity to cosmology. One was based in Princeton, and the other one was based in Moscow. And they worked often together, often in opposition with each other, and both developed the subject in a fantastic way. Professor Varun Sahni went to do his PhD in Moscow State, with the group that was headed by Professor Zeldovich. He worked very closely with Professor Starobinsky and did a lot of work on inflation. and the gravity wave, relic gravity waves from inflation, gravity wave contribution of inflation, all that seminal work was done at that time. Then Varun went as a postdoc to Canadian Institute for Theoretical Astrophysics, Toronto, and then Newcastle. I met him when I was a PhD student in Cambridge. Varun came to visit. This was 36 years ago. And he was then working on collapsing large-scale structures, pancakes, and all that stuff. That's the Moscow school. And it was wonderful to see the kind of work that numerically is being done and simulations of stuff. So Varun got into simulations. Varun got then into how to quantify the larger scale structures, brought topological and mathematical ideas into it, which led to things like shapefinders, which are essentially topological ways of describing the larger structures in the universe. Of course, Varun has done amazing work in defining the equational state of the universe, some of which we'll see today, and also working on just general large-scale structures of the universe, looking at what the structures look like in the universe. So this is his astrophysics as opposed to the cosmology, which was the early work on inflation and things like that. So Varun is a fellow of all 3 Indian science academies. He got the biggest award given to young scientists in India, the Shanti Swarup Bhatnagar Award. And we just learned yesterday that another of our members, Professor Saurabh Pal from chemistry, got the same year, the Shanti Swarup Bhatnagar Award. Varun is not just a physicist. He has quite a lot of other attributes. As I said, he's a rock star. He was a champion archer and writes amazing plays. Varun and I have acted in many plays together. I could have shown you some pictures of all those plays. Some of it there on YouTube. You can look them up. And so Varun and I worked in IUCAA for 12 years together. Varun, after coming back to India, stayed at IUCAA from the early 90s and retired a couple of years ago, and is still an emeritus professor at IUCAA. And in fact, I wrote my highest cited paper is co-authored with Varun. So it's a great privilege that I've written papers with him as well. But if you just look at some of his highly cited papers, you will see they actually are amazing seminal contribution and review papers on subject that he's going to talk about today, which is dark matter and dark energy. So it's again privilege to welcome Varun to the stage.
Thank you.
Now, Anjan, before he starts his talk, we wanted to, yes. Come, who's taking a picture? We need to show.
Oh, that's lovely.
So it's a plaque that we.
Oh, thank you so much. Beautiful.
Yeah,
Thank you so much.
So what I'll do is I'll keep this here and take it.
I heard it. Thank you. Thank you very much. Now, here's the point. We should switch off the lights.
Yes.
So thank you, Shomak, for this very generous introduction. It's sometimes embarrassing to know people from so long back because you know how naughty they were. And you can tell all kinds of stories, which I'm not going to tell today. So I'm going to tell you about all the excitement that is happening in cosmology, which has become a fantastic field. When I joined cosmology started doing my PhD in 1981, people said, why are you doing cosmology? Do particle physics. That's where the action is, right? I mean, do supergravity, do supersymmetry, right? But I stuck it with cosmology, and now it's the happening field, right? Gravity waves have been discovered, black holes have been discovered. It's just fantastic. Dark energy, dark matter. So I'm going to summarize some of those things that I find to be really exciting in the universe, right? So hey, why is this thing coming on the top, right? That should not be there. Dark matter, it's coming right here. Yeah. Oh, it's come down here now. It's come down here now. Come here, come here. Hello. Yeah, it's on, I think. You can hear me at the back? Yeah. Mic is on. Just this dark thing needs to go, but it's not going, is it? It'll go. We'll see. We'll see. So, one of the surprising things about the universe is that it consists of probably three main components. One is, how does this thing work? Yeah, I got it. So it consists of three main components: dark matter, dark energy, and normal matter, right? But of these, dark matter and dark energy just don't shine. They are dark, right? Okay. And evidence about them is quite indirect, but they are there. And only 4% on matter is in everything else that you see, in the stars, in the galaxies, in the intergalactic medium. Everything is just 4% of the total matter. So let's go to the next slide. Taking time. Yeah, I'm pressing the right one. It's not going. It's some conspiracy here. It's not working. It was working during when we tested it, but it's not working now. No. See, this one is not working, right? I press it, it doesn't happen.
Who press it?
No, but one has to have a button to press, right? Oh, this one. Oh, so I have to stand here then. Okay, cool. You see, this one is not okay.
Yeah,
Now it started working.
Just you need the sensor to be pointed.
Okay. Got it. Okay, that's also gone. Let me just press escape to. It's not still again, it's not working. You have to bring the cursor. You see, when I press this, it doesn't come. Okay, now also it's not coming. But it stopped. It's not working. The mouth, the thing is not working. It's not working. Navi Tharo. Let me see. Back. नहीं हो रहा. Loading. नहीं हो रहा loading. It's not happening. नहीं हो रहा. आप खुद ट्राई कीजिए. I can do it manually also. If it isn't working, nothing is happening. Wait. Let me try it. When I touch it, it stops working.
Yeah, that's working.
Yeah, okay. Okay, sorry about that. Let's keep fingers crossed and let's hope it continues. You know, on the scale of the universe, what does it matter a few minutes? Living here for 14 billion years. So the universe consists of three main components: dark matter, dark energy, and normal matter. And only about 4% of it is in everything else we see: the stars, the galaxies, the IGM, everything. So, as you all know, galaxies are the building blocks of the universe, and over 1 lakh galaxies have been mapped. And very soon, with Euclid and other LSST and all the big observatories going up, this number is going to cross 100 million, right? And galaxies come in many beautiful shapes and sizes. When I was a kid, I loved just to see pictures of galaxies. This is my favorite: Sombrero Galaxy, the Whirlpool Galaxy, and many others. But the astonishing thing here is that galaxies come in a large number of shapes. There are dwarf galaxies to giant ellipticals, and two questions arise. Did galaxies always exist, right? Or did they come into existence during the course of cosmic expansion? And the second question is, are galaxies distributed randomly in space, like this Poisson distribution? Or does the galaxy distribution have a structure? So let me attempt to address this point. And of course, as you all know, all these galaxies are moving away from each other, all right? And two galaxies further apart move further away faster. And this is known as Hubble's law, right? Discovered in 1929 by Hubble. And h is the speed of expansion of the universe. It's 70 kilometers per second per megaparsec. So if all the galaxies are receding away, and this is the present universe, then if you go back in time, these galaxies should have collided, right? If they had the same size as they do, right? Which means the galaxies could not, in an expanding universe, have existed forever. Okay, they must have come into being, right? And this conclusion is that galaxies should have evolved from some smaller entities. And currently, the preferred evolutionary scenario is that galaxies arose from very tiny fluctuations, 1 part in 100,000, which existed more than 14 billion years ago. These fluctuations grew over time, and several billion years after the Big Bang, these perturbations were large enough to form stars and galaxies. So this is what the universe looked like about 100,000 years after the Big Bang. This picture is very famous. These are perturbations. They look large here, but actually they are very, very small. These are perturbations in the background temperature. You might recall that the temperature in the universe today is 2.7 degrees Kelvin, right? And these are fluctuations in this temperature, 1 part in 100,000. So they're really tiny, tiny fluctuations, right? And so this is what the CMB looks like. And these perturbations, you know, through the Poisson equation, you can see that the gravitational potential, you know, in the early universe was very small, right? But it existed. If it had been zero, you wouldn't have formed anything. So this is a very crucial point, and it comes to us from the CMB, right? So this is known as gravitational instability, right? Gravitational instability is simply that, you know, gravity likes to attract, you know. So if I take this thing and I stand it here, it's stable, but the minute I perturb it, it falls. This example of gravitational instability, right? Because gravity attracts everything, right? So these perturbations were tiny, and then they became large and turned into galaxies today. So that answers the first question, did galaxies always exist? No, they did not. And the second question is, are galaxies distributed randomly in space? So do they look like this, somewhat like the stars that you see at night, or do they look like this? And this picture is very important. This is the first CFA slice, Center for Astrophysics. And, they asked the question, well, you see, when they discovered the slice in 1982, people were puzzled because they said, well, maybe, our eye is programmed evolutionary to see patterns, right? I mean, look at Orion. This is what you see, and this is what you make out of it. Now, you need to have some imagination, to go from left to right. But people in ancient times had a lot of imagination. And the reason they had a lot of imagination was the following, right? That, if you couldn't spot this tiger in the jungle, you were going to be eaten up, right? So even if you see a fictitious tiger in the jungle, that's still okay. Or, in India, a snake in the grass, right? You better be able to spot that snake, right? Otherwise, it's over for you, right? So somehow over the 100,000 years of evolution, you learn to spot patterns, right? Even when they were very vague. So this was a debate when I entered cosmology. I was starting my PhD in 1982, and this structure was seen, and they were wondering, this is a stick man, sometimes called the stick man, right? Over here, right? And then observations got better and higher redshift surveys, and here, this is now known as the cosmic web. It's like the web of a giant spider. I know the person who coined this name. I can tell you later. It's very interesting. And as more and more galaxies came, you found that this web got much denser. And you realize that there are superclusters of galaxies, right? Until about a decade ago, this CFA Great Wall, this is known as the Great Wall, was the largest structure in the universe, and its size was roughly 100 megaparsec, which is a third of a billion light years across, right? And it was as large as the survey extent. So you didn't know whether this is a typical object or whether the largest objects exist. And since matter, there's a conservation of matter. So if you push matter in one corner of space, the other corner becomes empty. So you also had large voids, regions where there were no galaxies, right? So this is the northern hemisphere and this is the southern hemisphere. And you can see large supercluster running here too, right? And so a decade after that, the Sloan Digital Sky Survey came online, and you found there were even larger superclusters. Look at the size of the wall, and this is the Sloan Great Wall. And it's one of the largest known structures in the universe. It's 1.37 billion light years distant from us and 1 billion light years across. So we are looking at really large scales, right? And so matter is distributed coherently in this enormous filamentary or pancake-like structures. And I should add that Professor Raychaudhuri started his PhD by working on a very important supercluster called Shapley. We were in Cambridge together, and he used to describe this beautiful object to me. And more recently, he's also worked on the Saraswati supercluster, which is another important supercluster. So we live on a cosmic web consisting of galaxies, clusters of galaxies, superclusters of galaxies, which are separated by large empty regions called voids. And here's another map of another supercluster called the IUCAA supercluster. It was discovered it's the home to our Milky Way. So we are part of this gigantic structure, right? And it was discovered in the observatory in Hawaii by Brent Tully and his collaborators. And so they took the Hawaiian name, IUCAA, which means immense heaven. And you can see what a beautiful percolating supercluster it is. And some of you might see resemblance with neural networks out here, right? And this could very well be neurons in the brain, right? So, another picture here which summarizes this is this one. This is the local concentration of superclusters with IUCAA shown in yellow. So we are somewhere here. Virgo is the nearest cluster to us. And you can see IUCAA here, and here's the Shapley supercluster which Shomak worked on. And it's very interesting because you can jump from one supercluster to another and from here to here to here to here to here, right? And so what has happened is that due to these, yes. So this is a rough picture now. The outline of gravitational instability is that tiny fluctuations, 1 part in 100,000, grow into a very non-Gaussian density field, right? Which delta rho by rho, the density contrast is more than 1 million now, right? It's definitely over 1 million in the galaxy. So initially the density field was almost a Gaussian distribution. Gaussians, as you know, are very popular in statistics, right? And so this is a simulation of an n-body simulation of large-scale structure. And you start at redshift of 50, I think, when the universe is very smooth. And as you evolve to today, which is redshift of 0, you see that gravity pulls all these objects together, and you get these giant filaments and giant voids. All right. So this is a picture of what the universe might have gone through. Of course, this time scale is 14 billion years. So those of you who think this is a very complex process, let me assure you it is not, right? See, the caustics that you saw, right, the cosmic web, right, are very similar to the caustics of light. So all of you have seen these pictures in the swimming pool, right? Yeah, when you go swimming sometimes, you see bright and dark spots, right? And actually gravity behaves like light. This is remarkable, absolutely. And I think I had another transparency here, yes, this is the one, right? So, I skipped some. This was the one, right? So the formation of high density distributions, high density regions in the distribution of matter is similar to cosmic web, right? These are the caustics in the distribution of light. And this parallel was actually discussed by Zeldovich. So what do you see in the motion of light rays? So suppose I have a light ray and, light is made parallel, it enters this, this lens at location Q, and this is the thickness of the light plate, but it is not a uniform thickness, right? H varies with scale, right? It varies with Q, right? Q is this axis. And so what happens is when light emerges from here, it is deflected by an angle, and the angle is simply the gradient of the thickness H. So you will have different neighboring trajectories focusing and forming what are known as caustics. So if this is a swimming pool, this would be the thickness of water on a. So if the wave of a wind blows over the pool, the surface of the pool is perturbed, and you get these pictures. Right. Now there is an exact parallel because this is the equation for the caustics in water. R is equal to Q plus S times Z. Z, if you recall, was the distance to the plate, right? This was Z. H is the thickness. Q is called the Lagrange coordinate. And over here, you have exactly the same equation. R is equal to Q. And this quantity V is the gradient of the gravitational potential, right? Which I told you from CMB, is 10 to the power minus 5. These are tiny fluctuations. And as the universe passes through these fluctuations, D is just a function of time. So the gravitational potential phi plays the same role as the thickness H in optics. So it's a one-to-one correspondence. This was made by me on a computer in IUCAA, and this was a photograph taken of a swimming pool. And if you see, even the details are similar. Some of these caustics that you see here and here are forming right here. This caustic is the same as this. And there's a very beautiful theory on the mathematical theory of caustics developed by Arnold and other mathematicians, right? There's an analogy between this and catastrophe theory also. It's a very beautiful topological area to explore. So that was an aside. And currently, the precise location of about 1 million galaxies is known, but this is going to change very soon. And those of you who are very young are going to be very lucky because this revolution will happen right before your eyes. And there's a very big surprise that the visible matter in the cosmic web accounts for only a small fraction of the total matter in the universe. Most of the matter does not shine. It consists of dark matter and dark energy. So this is the picture I had shown you earlier. So let me elaborate on dark matter. Again, two questions arise. Where is it and what is it? All right. Where is it and what is it? So how do we determine dark matter since it does not shine? Right. So the evidence of dark matter is indirect. Measuring the velocity of stars and neutral hydrogen in a galaxy, we can determine the depth of its gravitational potential. And this implies a need for dark matter. Okay. It's a bit like, so I'll come back to this, right? So there are 3 or 4 compelling reasons for the existence of dark matter. One, I will talk in detail. It's just from individual galaxies. The earliest was the observation that galaxies of clusters were not virialized. There's a beautiful theorem called the virial theorem in mechanics, which tells us the kinetic term is roughly half the potential term, the mean value of the kinetic term. So there are lots of objects interacting. You expect this equality to hold. And Zwicky showed in 1933 that it certainly does not hold in nearby clusters, which implied that if the clusters are gravitationally bound, you need a lot of dark matter. Right? So this was the first indirect evidence for dark matter. The third one is structure formation. You will never reach from this stage to the nonlinear stage only with baryons. Baryons cannot do the job. You need dark matter to accelerate structure formation. This is essential. Sometimes this is not emphasized, but it's true. And I'll go to the bullet cluster here later. So dark matter in galaxies, right? Now, supposing we all know we orbit around the sun and Kepler got those beautiful laws and Newton elaborated, but suppose the sun switched off. One fine day you woke up, there was no dawn. Could you still infer that the sun is there? And if you're clever enough, even if you're an undergraduate in Ashoka, I'm sure you're very clever, you could. Because by seeing your motion with respect to the other stars over the year, you could see that you were going around something that is very massive. And you could even infer, and remembering Kepler's laws, was the masses, even though it does not shine, right? And that is precisely how they find black holes, right? The huge, enormous black hole, million solar mass black hole at the center of the galaxy is discovered that way. You won't believe this, but stars near that black hole travel at 1/10 of the speed of light. Right? So you got this star whizzing around something that is not there. Okay. So this is the method that was used to determine dark matter in galaxies. So here's a galaxy, and you use Kepler's law, centripetal force balanced by gravitational attraction, and you get V is equal to square root gm over r. All of you know this. So if the mass is constant, if this is the visible part of the galaxy, and the mass is only here, then you expect the velocity curve to drop off as you go to further and further regions from the center. This is the center, right? But in fact, what is seen as V is constant, right? This is a rotation curve. This is known as the rotation curve. So this difference is attributed to the presence of dark matter. And it's quite surprising that it implies that matter grows with radius, and they've never really seen until where this halo extends. That's an important open question, right? So this is what the galaxy looks like, not only ours, but lots of other galaxies. The rotation curves have been measured for over 1,000 galaxies. Almost every galaxy has a dark matter halo. And this is the galaxy, the disk. These are the globular clusters surrounding it. And this is the dark matter extent, right? And the ratio of dark to luminous matter, this is m/L, actually grows from spiral galaxies to low surface brightness galaxies and dwarfs. In fact, this is enormous in dwarfs. Dwarf galaxies are dominated by dark matter, even in the central regions. So people who want to probe the nature of dark matter often appeal to dwarf galaxies. And the Milky Way is surrounded by 30 dwarf galaxies, Andromeda by another 30. So this is called the local group. In fact, one of those galaxies actually falling towards us. We kind of ripped it apart. It's known as the Sagittarius stream. Right? So Shomak knows all about this. You can pester him with this later on. Right? So the second, I told you that dark matter is non-baryonic. How do we know it's non-baryonic, right? So this is not just a postulate. This is a fact because, and more recently, it was confirmed by this enormous collision between two clusters. Now, each of these clusters has about 1,000 galaxies, 1,000 to 10,000. And these are very rare events, right? They're very rare objects, 1,000 galaxies in one spot. But all of a sudden, rare events, but they collided, right? Now, when they collided, something very interesting happened. There was the galaxies and the baryonic matter in the cluster, right? Consisting of intra-cluster gas, and that went through a shock wave. Okay, as the two galaxies clusters collided. This is the Bose shock that you see, right? This is the Bose shock that you see. But you could also find out something about the total matter content by seeing distant galaxies in the way they were distorted. This is known as weak lensing. I don't have time to talk about it, but you can see the entire dark matter profile, the entire matter profile. And this is astonishingly, they found that this is dark matter was located here. So when the two galaxies collided, boom, the baryonic matter started stalling because of pressure, but the dark matter went through as if it had not seen anything. which tells us that dark matter is not interacting with normal matter, right? And it's probably non-baryonic in origin. But theorists knew this long ago because non-baryonic matter comes from Big Bang nucleosynthesis and the CMB. Both of them tell you that the baryonic fraction is just 4%. And this, I teach this to my students. These are the nuclear reactions that take place a minute after the Big Bang. There's a lot of tritium being created. Deuterium. Deuterium is very sensitive. The presence of deuterium, the creation of deuterium is extremely sensitive because it's very difficult to make and very easy to break. Its binding energy is just 2 MeV. And so it's a very strong function of the baryon density. And if you want to get the precisely correct value of deuterium you see today, you do require that the baryon density is 4%. So this is really correct. So now let me go on to the next question. Now we know where is it, but we don't know what is it. Right? So what is dark matter? So there are 3 categories of dark matter have been suggested. When you are young people, you can suggest a 4th or a 5th. The first one is WIMPs. These are the oldest category of dark matter. WIMP stands for weakly interacting massive particles. These could be massive neutrinos or supersymmetric partners of standard model fields. Essentially, you need to extend the standard model because the standard model does not have room for dark matter. So these are elementary particles. We still don't know what they are, but it's very important candidate. The second are MACHOs, massive compact halo objects. These could be failed stars like Jupiter's or black holes. Recently, after the discovery of black holes, this MACHO possibility has gained in importance, right? And the final one is the oscillating scalar field. Just have a scalar field, Higgs-type scalar field, just oscillating everywhere in the universe, including this room. You will get dark matter. So let me discuss this. So this is a very important question, what is dark matter? Because high-energy physicists need to know the answer in order to know in which direction to extend the standard model. We know the standard model is incomplete, right? We know there are questions the standard model is not answering, right? There's a mass of the neutrino, for instance, and many other questions, right? Hierarchy problem and all. And the cosmologists need to know the answer to answer key questions. When did the first stars and galaxies form? Right? When was the epoch of reionization? So in 66 was a key year because Gersten and Zeldovich showed that if the neutrino was massive, it could dominate the universe. And this paved the notion for non-baryonic dark matter. Now we know, of course, that left-handed neutrinos can't do this, but a sterile right-handed neutrino might, right? So I'll just go through this argument very quickly, right? Just a second after the Big Bang, a lot of very interesting processes are happening, right? And some of them involve the neutrino, production of neutrinos. So the E plus, E minus, positrons and electrons can collide and give rise to neutrinos. The neutron decays giving rise to neutrinos. Electron interacts with proton giving rise to neutrinos. And so we have today a Rayleigh number density of 108 neutrinos per centimeter cube, right? Right. So how many neutrinos are passing through my hand? How many? Student, please tell me, how many neutrinos are passing through my hand? Louder. No. Trillions. Trillions are passing through my hand because of the sun. And sun is below the horizon, so they're coming from there. But if I subtract all these trillions of neutrinos that are coming from the sun and from the stars and from every other thermonuclear reaction, I am still left with a Rayleigh abundance of 108 neutrinos per centimeter cube. That's like a ping pong ball, right? Now, the remarkable thing is that if you give each of them a tiny mass, only 15 eV, you get all of dark matter. All right. And this is what Zeldovich realized. And I was in Moscow when they did an experiment on double beta decay, and they discovered that, oh, wow, it's 15 eV, and there was a lot of excitement. That summer, it was Olympics in Moscow, 1980 Olympics. The Americans had boycotted it. The Russians told us, get out of here. I went to Berkeley, and I met Joe Silk, and he was working on exactly this picture, hot dark matter. Zeldovich wrote a paper, Joe Silk wrote a paper. It was a very exciting time in science. But the experiment turned out to be wrong. And it was a tough experiment to do. I don't blame them. And now we know that the neutrino has a mass. That's very important. From neutrino oscillations, it has a mass, but the mass is less than 1 eV, so it cannot play the role of dark matter. But the origin of this mass is very important for particle physicists, right? So now people feel that, just like in this interaction, you got neutrinos coming from annihilation processes in the early universe. This process froze out about a fifth of a second after the Big Bang, right? But there could be many other processes which gave rise to a stable dark matter particle, right? And these are WIMPs generally. And so the search of WIMP dark matter has taken several forms, production in dark matter in collider searches. This is the best, the way you found Higgs 11 years ago, bang things together, discover dark matter. People have been trying it, they have failed, unfortunately, right? The other is indirect detection through dark matter decay or annihilation. I mean, if dark matter is everywhere and it's decaying into something else, right? Or self-annihilating, if it's a Majorana particle, then you should be able to see decay products, right? This is astrophysical. The other one is just direct detection on Earth, right? So you take, there are very large underground experiments. Lux was giving, until a few years ago, the most stringent upper bounds. So this is the WIMP nucleon cross-section. If you believe that the WIMP is interacting, the WIMP has to interact with matter to be detected, right? So if you assume that it's interacting, weakly with using the weak force, this is the interaction cross-section. This is the WIMP mass. This is the mass required to give dark matter, GeV, right? And you find that Lux gave very stringent upper limits on this dark matter content, right? And more recently, this has been, further developed by the Xenonit experiment, right? And now it's gone even lower. So there has been no real detection. This is just a year old of dark matter. So if dark matter is abundant, it's interacting very weakly, or it doesn't belong to this mass range. All right. So now people are a little perplexed, right? Because, about a decade ago, they were pretty sure that Lux or one of these experiments will detect dark matter, but now it's not detecting, right? So they say, all right, desperately seeking sterile, right? So they're saying, well, neutrinos have mass and they oscillate between each other, and there's the seesaw mechanism that, can give rise to these oscillations. So maybe there's a very large, very massive neutrino, right? But it is right-handed, and so it does not interact with the weak force, interacts only via gravity, right? And this is known as the sterile neutrino. And in recent years, this model has become quite fashionable. In fact, what happens to the sterile neutrino is that it actually decays to a neutrino and a photon. And since if you have a keV neutrino, it will give off a 3.5 keV line, which is in the X-ray band, right? And so you believe that, well, you should be able to see, these neutrinos are abundant. They're everywhere. They'll be in this room. They'll be everywhere, right? And so, there was a lot of excitement in 2014 when Vaidya-Raychaudhuri and others reported in a PRL paper that they saw exactly this line in Andromeda galaxy and in the Perseus galaxy cluster. Then Bulbul et al. Stacked 73 galaxy clusters and found precisely this line. But then a controversy arose. No such line was seen either in the Virgo cluster or in the Milky Way. And then people said, wait a minute, this line is compatible with the emission from atomic transitions of potassium. So now it's not clear, right? Did you see neutrino decay, or did you see just astrophysics, right? So this is where the situation stands. I'm not going to talk about this. So then we come to another possibility that it's an oscillating scalar field, or it may consist of black holes. So why an oscillating scalar field? Oscillating scalar field, you see, scalar fields are not ubiquitous, right? Theoretically at least, right? If you believe in inflation, then people believe it could be a scalar field. Higgs is a scalar, right? Any scalar field with this kind of a minimum, and remember, if you Taylor expand almost any function around the minimum, you get m squared phi squared, right? That's the lowest order expansion. If this field is oscillating and it has to oscillate, then during oscillations, the mean value of the equation of state, and the equation of state is simply W is the pressure divided by the density. This is the equation of state, right? So if this is 0, then it can behave like dark matter because it has no pressure. And no pressure means that anything can just collapse, right? If it has pressure, then it will stop things from collapsing. So it behaves just like dark matter. And, it can even, anyway, I'll skip this, right? So how do you get these scalar fields, right? And I'll give you one very exotic possibility, right? Now, you all know that, 10 years after Einstein developed general relativity, all right, Kaluza and then independently Klein developed a 5-dimensional theory of gravity. And they showed that, look, this is a really beautiful result. That if your 5th dimension is compactified, if you roll it into a tube and make the tube really small, then what emerges is 4-dimensional gravity, which is general relativity, plus an electromagnetic field, plus a scalar, which is nowadays referred to as a dilaton or the radion. Radion because it's related to the radius of the 5th dimension. So any kind of compactification generically leads to the production of scalar fields. In fact, Einstein was very happy with this Kaluza-Klein paper because, at that time people wanted to unify electromagnetism with gravity, right? Einstein worked a lot on this in his later years, right? Geometry, there was a geometric unification. And so now the thing is that, you have theories like string theories that live in 10 dimensions, and we can't jump into an extra dimension. So maybe those dimensions are compact. And if they are compact, you might have this kind of a dilaton that is escaped. A dilaton field that is present. But let me come to the other possibility. The dark matter could also be in the form of machos. Now, instead of being smooth, scalar fields are smooth, WIMPs are smooth, black holes are clumpy, right? So now you'll have dark matter, which is clumpy and not smooth, right? So just a small revision, you all know how a black hole forms, right? You see in a normal star, the pressure is balanced by gravity. But if somehow this pressure switches off, when the thermonuclear reactions switch off, and as the star dies, it just sheds its outer envelopes, and it can evolve either into a white dwarf or into a neutron star. If it's very massive, then it collapses into a black hole. This is the standard, physics behind black hole formation. And now the very amazing result is that, if you were studying black holes way back in 1960s when I was doing my PhD, and I really wanted to study black holes at that time, people would say, please, go and read H.G. Wells, go and read science fiction. Like, science mein kya kar rahe ho, right? Do something real, And now if you're not doing black holes, they'll say, kya kar rahe ho, bhai? This is the mainstream, right? So often, sometimes, you are ahead of the time, right? So people who were working on black holes in those days, Roger Penrose, Kip Thorne, have now got the Nobel Prizes for their outstanding work. And one of the most sensational discoveries of the last decade has been the merger of 2 black holes, which all of you know about, and the liberation of energy in the form of gravity waves. Right? This is an amazing discovery. We covered it in Chandrasekhar Auditorium, and Shomuk was the director. It was the most thrilling experience of my life. And so now you know that what is happening here is that 2 smaller black holes, right? And they're not too small, 40 and 30 solar masses are merging into a large black hole. These are 3 LIGO, the first 3 LIGO black holes, and there are many more now. The last count I was checking was 83, right? And this is just discovered by Google, by LIGO and the Virgo Consortium. And soon the Indian Gravity Wave Consortium will be up, and Kagra, the Japanese one, is measuring, and you're going to have a plethora of black holes everywhere. So you can ask, what are the size of these black holes? So if these 2 merge to this one, and this is Maharashtra, so you can see, you don't want to go too near this big object, right? This is the scale, right? But imagine this 60 solar mass black hole, it fits into such a small space, right? That should kind of impress you, right? So now the question is that, aside from these astrophysical black holes, which are, 3, 4, 10 times larger than the sun, black holes can also be very, very tiny. Very tiny. And this is the idea of primordial black holes. Right? So primordial black holes, just like WIMP dark matter, right, or scalar fields, could have been formed just shortly after the Big Bang. They can be massive, but also very tiny. So what is the scene here? The question is that if our universe consists of black holes, forget about it. They are tiny or they are large. How do you detect them, right? You detect them during coalescence, but how do you know they make up dark matter? And the answer here is that, again, you use an indirect effect. And the indirect effect is gravitational lensing. See? So you know that gravity bends light, right? So normally light travels in a straight line. If there's a massive object, the light bends, right? And so this was, if the star was over here, it'll be bent and you'll see it over here. And this was actually the original method used to test, Eddington used it to test general relativity in 1919. Amazing, this was the time of the First World War, right? And Einstein was a German scientist. Eddington was a British scientist, and they were at war at each other, but in science they collaborated. That's why I love science. We go beyond these stupid political boundaries, right? You're like one sisterhood or one brotherhood, right? So you do the same thing for a black hole, right? Suppose you have a black hole and you're living over here, and there's a star, this star could be far away, and a black hole passes in between you and the star. What's going to happen? The star, the light, this is going to act as a gravitational lens, right? So it's going to focus the light from the star onto the Earth. And so the star will look brighter, and then it'll look dimmer again. So if you keep, this is known as microlensing. You keep looking at different stars, they could be in the Andromeda galaxy, and you see if some of them suddenly become brighter or darker. And in fact, there were 3 events that were detected by Macho, and they caused a lot of excitement. So let me give you a whole picture now where we stand. So microlensing and other constraints, right, paint you this picture of the universe. This is the primordial black hole mass, or mass of black holes. This is in terms of the solar mass, right? So the LIGO, Virgo black holes are here. But this is the y-axis is the relative density of black holes to dark matter. So you want this to be unity if black holes form all of dark matter, right? And you know that the mass gap here, it is possible, but it is possible only for very tiny black holes, right? These black holes are really small. The black hole over here has an asteroid mass, and this black hole over here has the size of a hydrogen atom, right? So this is a really tiny black holes, right? This is the window where black holes can constitute all of dark matter, right? And how does one form so many black holes? So let me go back to this because I find this intriguing. You see, primordial black holes can have this range, right? And the radius of a black hole is just 2 gm over c square, and m solar is the mass of the sun, right? So if you have a 10 to the power 21 gram black hole, it will have a radius of only 10 to the power minus 6 centimeter, which is the size of a small dust particle and smaller than the wave light. And such a tiny black hole will still have the mass of an asteroid, and it'll be somewhere over here. So the mass of the galaxy is 10 to the power 45 grams. So the number of black holes constituting the dark matter is 10 to the power 24, right? This is a huge number, right? So my question is that suppose you accidentally inhaled such a small black hole. It's like a dust particle. What will happen to you? You can go back and think about this, right? Because if there are 10 to the power 24 black holes surrounding the galaxy, the chances that in the canteen somewhere what you inhaled was not masala. So these tiny black holes cannot form astrophysically. That's quite clear. Only large black holes can form astrophysically. How do you form them? And the answer, you form them in a process called inflation. And this was a very important work done by Zeldovich and Novikov and Hawking. And they said that following that, look, the universe has a horizon. The horizon is just c times t. T is the time since the Big Bang. That's the furthest we can see. And if you can form a perturbation of order unity on the scale of the horizon, no pressure effect can stop it from collapsing into a black hole. And you can see how far back these people were thinking, right? And the horizon gets smaller and smaller as you go back into the past. So you've got to compress things in much smaller regions of space. So the primordial black hole mass is related to the solar mass divided by the 1 plus z factor, right? So you go back to the time of 1 second after the Big Bang, QCD phase transition, you get solar mass black holes. You go back further, you get tinier. And the point is, how do you get it? You get it using inflation. Inflation is kind of the mother universe. The universe grows exponentially. Quantum fluctuations generate the galaxies, dark matter and dark energy, and finally the cosmic web. So this is the result, and this is a little technical over here. So you can generate fluctuations during inflation, and then inflaton field possesses features like bumps or dips in the potential, right? And when these fluctuations re-enter the horizon, you get primordial black holes. So this is inflation. Inflation is very interesting because, recall, small scales are stretched exponentially, right? So what is happening is that your expansion factor, is going something like this, is going like e to the power, there's an integral h times dt, right? So it's growing exponentially, right? And there is, if you combine all the masses, the fundamental constants, right, you get something known as a Planck scale. Right? The Planck scale is tiny, it's 10 to the minus 33 centimeters, right? So this is where you expect quantum gravity effects to become important. And the wonderful thing about inflation is it can stretch 10 to the minus 33 into 10 to the minus 3 easily. And that is already macroscopic scale. So inflation has this beautiful property that it can generate quantum fluctuations, right, which later give rise to galaxies. Okay. So this is a model that we developed with my PhD student Swagat, right, and became very popular. Normally, this is the inflaton field. You can imagine this to be some kind of scalar field like the Higgs, but it's not the Higgs really. And if it just rolls down, you will get the seed, this is the power spectrum of perturbations, and you get the normal, what generates the CMB, right? But if you have a tiny bump, then as the field goes over the bump, it slows down, and it has to slow down just a little bit to get this enormous bump. And what this does is it compresses scales on the horizon scale. It compresses all those large scales into black holes, right? And so you get this picture that, scales that exit the horizon earlier on re-entry give the tiny fluctuations you see in the CMB, and scales that exit the horizon later, enter the horizon later, give rise to primordial black holes. And there's an enormous difference in amplitude, right? So this is one possibility of creating very large primordial black holes, which can give rise to all of the dark matter that you see. So actually, you have to solve the Mukhanov-Sasaki equation, but I'll not go into details of how you do that, right? And I was going to skip over this, but I'll just mention this for the experts, that remarkably, if you have such large fluctuations to give rise to black holes, they'll also induce a secondary gravity wave background, right? And this gravity wave background has just been detected, right, by the nanograv observatory in using the pulsar timing arrays in the US and in other countries, in India also. And it is remarkable that they found gravity waves with a very tiny amplitude, and look at the frequency. It's just one oscillation per century. So the wavelength of this gravity waves is 100 light years. So now you're sitting here, and our entire solar system is being deformed and stretched by this huge gravity wave that is going through it's the longest wavelength and the slowest gravity wave ever. And we don't know how it is produced because standard models using black hole production run into serious trouble when producing this kind of a gravity wave. And the interesting thing is that if you do cosmological perturbation theory, this is simply Landau-Lifshitz, volume 2, classical theory of fields. You know that you can have vector, scalar, and tensor perturbations arising in the early universe, but they decouple completely, right? But at higher order, the scalar and the tensors couple. So if you have a large scalar perturbation, you can induce the gravity wave. There's a beautiful review here. And this is a bit about the gravity waves. And in fact, I picked this picture up from a paper from a Jamia group who did analyze our model and showed that it fits the nanograv results pretty well. So this could be very exciting. All right. To summarize, dark matter might be WIMPs, machos, or scalar fields, but there's no experimental confirmation for any of these possibilities. But if the nature of dark matter is elusive, then the nature of dark energy is very, very positive, right? So what is dark energy? It's one of the most exciting observational discoveries. The universe is accelerating. the source responsible for cosmic acceleration is just unknown, so we call it dark energy. Right? And the remarkable thing is that dark energy has a negative pressure. So I told you that if you have zero pressure, you get dark matter. Negative pressure gives rise to dark energy. So this is a very beautiful paper, 1998, in Nature. Exploding stars point to a universal repulsive force. And I'll read it out to you. The universe could be permeated by a large-scale repulsive force. The reservoir of energy fueling that force could be anything from a quantum mechanical shimmer, called the cosmological constant, to even more exotic possibilities, right? It was based on a total of only 44 far-off supernovae. And people commented, it is a magical discovery. What it means is that there is some form of energy we don't understand. Right? These are big words. Mike Turner was at that time head of the Astro Lab in Fermi Lab, right? So subsequently, the lead people in the discovery were awarded the Nobel Prize for Physics. Now, I won't have time to talk about how this discovery was made, but if dark matter can be understood entirely within the framework of Newtonian gravity and a bit of gravitational lensing, to understand dark energy, we need to turn to GR. Okay. All right. Okay, fine. So let me go into this, right? So everybody's familiar with Poisson equation, right? Yeah, this is the Poisson equation for gravity. But if you include general relativity, this changes to del square phi is 4 pi g rho plus 3p. So pressure carries weight in Einstein's theory. This is very important, right? Pressure can modify the expansion of the universe. And if this term turns negative, it's like G changing sign. And gravity becomes repulsive. Okay, that's one way to understand it, right? So you have repulsive gravity, and the most popular candidate for repulsive gravity was the cosmological constant. So your energy momentum tensor has this form, which implies a negative pressure, all right? And the density remains constant, remember, right? It's a constant as the density in other forms of matter decreases. So you have something like this. Normal matter is decreasing, lambda remains the same, okay? So then immediately a question arises that why are the two densities comparable today? This is sometimes known as cosmic coincidence, right? If lambda was very large in the past, the universe was accelerated long ago, there would be no galaxies at all. So today, these are the latest observations. So it agrees well with observations, but you can have other models as well. So this is another way of looking at it. You rewrite these equations into this form. This is just the radius of the universe. This may look complicated, but if you define mass to be 4 by 3 pi r cube rho, then this looks just like the force law. Acceleration is force, gm over r square with a minus term plus lambda over 3r. So clearly you see an attraction due to normal matter, and a repulsion due to cosmological constant. So you find that cosmological constant gives rise to a repulsive force whose value increases with distance, right? So this is what it looks like. You can actually get all these equations from simply d minus pdv. So earlier on, this term dominates because of 1 over a cube. So the universe was decelerating. Today it's accelerating, right? And we live very close to this epoch, right? So this is like a universal tug of war. This spring is dark matter, and dark energy is getting more and more powerful because it remains constant. Okay. And today we live in the special epoch. So what is the cosmological constant? What is it, right? So there's a nice history here. In 1917, just 4 years after he had discovered general relativity, Einstein proposes a cosmological constant. He rewrites his equations with lambda. And in a letter to Ehrenfurst, Einstein writes, I've again perpetrated something relating to the theory of gravitation that would endanger me being committed to a madhouse. So Einstein is saying this, that look, I made this completely crazy discovery, right? Even he found it to be strange, right? In 1917, de Sitter presents vacuum solutions of lambda containing lambda. In 1922, Alexander Friedman. So Einstein actually wanted to make a static universe. He liked a static universe, so he introduced lambda for that reason. But in 1922, Friedman showed that you can get expanding universe solutions. And in 1923, Einstein was a very humble person. He didn't stick to his ideas. He said, well, if there's no quasi-static world, then away with the cosmological terms, right? And much later, discussing things with George Gamow, he said that the cosmological constant term was the biggest blunder of man's life, right? And it's quite remarkable that something that Einstein threw into the trash can became center physics 100 years later. So even the minor ideas of great people sometimes carry a lot of importance. So after Einstein discarded lambda, I call this the wave of lambda, the wave of interest in lambda, right? So in 1917, the interest in lambda peaked. Einstein said, no, expanding universe. Very few people worked here. This is like vacuum fluctuations, right? In 1967, people had developed quantum field theory. And bang, lambda came right into the center fold of modern physics. And today is dark energy. So this wave of lambda is very interesting. This is where we are living now. And this actually coincided with the wave of interest in extra dimensions. In 1921, Kaluza and Klein proposed extra dimensions. In 1970s to 80s, the modern Kaluza-Klein theory was born. And now you have string theory and the Randall-Sundram model. Right? So I think the birth of the second revolution in lambda was made by various people, but including Zeldovich. And he showed that the vacuum is actually seething by the activity. And the equation of the vacuum is exactly P is equal to minus rho. So this is the equation of state of the cosmological constant. It is P is equal to minus rho, which implies that W is minus 1. Right? And so Zeldovich said a very remarkable thing. He said, well, the genie, which is the cosmological constant, has been let out of the bottle, and it is no longer possible to force it back in. This is remarkable. This is 1968. There was no dark energy at that time. So since then, this is exactly what Zeldovich was saying, that look, the vacuum has these E plus E minus pairs, right? They are there in this room, and they all gravitate because all of matter gravitates, including the vacuum, right? And this vacuum has this equation of state. And the vacuum has been confirmed, there are various effects, including the Lamb shift, right? So we know this picture holds, but there was a problem. If you integrate, I can tell the students later how you get these equations. If you integrate it, you get a ultraviolet divergence. So the vacuum has infinite energy, whereas what you see is very tiny. So why is this enormous mismatch between what is predicted and what is observed? So here's the energy of the quantum vacuum. Observed is tiny. Field theory formally gives infinity. Quantum gravity may lead to a cutoff at the Planck scale. The supersymmetry make it smaller, but we don't know what's happening. So this is a nice poem quoted by Weinberg in this beautiful review. As I was going up the stair, I met a man who wasn't there. He wasn't there again today. I wish he had stayed away. So the problem in 1998, pre-supernovae, why is lambda 0? You expect it to be there. Why is it 0? You see, there's no symmetry in the universe. There's a U1 symmetry that guarantees a photon has no mass. But there's no such symmetry in the weak theory. So the neutrino has a mass, right? And there's no such symmetry in fundamental physics. So lambda needs to be there. But why is today we are asking, that time they were asking why is lambda 0? Today we are asking a harder question, why is lambda so small? And you can generate small values of lambda. For instance, we wrote this in our review. If you take a huge scale, the Planck scale, and take e to the power minus 2 times the fine structure constant, you get exactly the value of the energy density you see today, right? But how to get it from theory? This is kind of numerics, right? Okay, I'll try to, right? So the cosmology, you guys took a lot of my time fixing the computer. You have no right to talk. Quiet. I was seeing the time, how the clock, now you're seeing the time. You saw the time then? Okay, my clock here is working very well. So the cosmological constant has not yet been resolved. But a tiny cosmological constant like we encounter can encounter an initial conditions problem, all right? And that is the following, that if lambda stays the same, then what set the initial conditions for lambda? Because this ratio is going to be tiny at the electroweak scale. It's going to be really small. And if you extrapolate it to higher densities, it's going to be even smaller, right? So people have proposed evolving dark models of dark energy, right? The dark energy is today appearing to be constant, but it was in the past evolving. And there are 2 models I'll briefly mention, right? And I'll go from the undergraduate perspective. All of you know the point particle Lagrangian, right? All of you know this? You've seen this? Great. So if I substitute for R, a scalar field, you get half phi dot square minus V. This is known as the quintessence Lagrangian. And clearly, the pressure is negative. It allows cosmic acceleration. So you can construct it very simply, just from the classical point particle Lagrangian, but you can go to the relativistic particle Lagrangian, right, which looks like this. And again, do the same transformation. B goes like R dot, right? And R goes like phi, and you get this Lagrangian, which is known as the Chaplygin gas Lagrangian, which Anjan Sen has worked on and Sumashri have worked on extensively. And again, pressure is negative, right? So you can get very simple Lagrangians in which dark energy is evolving, right? And here's another picture of what can happen if you have a tracker model. So dark energy can initially behave like radiation, then like matter, and then become small. So people are wondering now, what is really going on with dark energy? Was it large earlier, or was it fixed to the cosmological constant value? This is a very hot game right now, right? People are wondering, is it dynamical quantity or is it not? Okay, there's another way of making the universe accelerate, and that is to modify the gravity sector. Right now, we were playing with the matter sector. They're saying modify the gravity sector. So which means that, here you modify matter sector, here you're playing with gravity. And this is very nice because Starobinsky was the first person to show that if you add a simple R square term to the Einstein-Hilbert action, you get a cosmic acceleration. This is the first model of inflation. And it worked very well. All right. So people suggested the same thing that, well, if this is not an R square, put in 1 over R, this will change, expansion at low values of R, which is today you can get cosmic acceleration. But this has ghosts and all kind of problems. But this is one direction people are working in. My time is short, so I will skip this. People are also worried about, suppose you have normal GR and an extra dimension, maybe you can get. So this is another picture that our universe is actually membrane embedded in a higher dimensional bulk spacetime, right? So in this case, you have two possible compactifications, a small compactification, which can give rise to dark matter, but the universe could be very large. And this is the picture that science fiction writers use, right? So this is a fifth dimension, and you can construct a wormhole through it, right? I worked on these theories, right? I worked on these theories, and one of the simple ones is, this is a brane world. You have the 5-dimensional gravitational constant, the 4-dimensional gravitational constant. You divide the two, you get a length scale. And amazingly, the length scale turns out to be the Hubble radius if the two mass scales are very large. So you've got a 100 MeV mass scale here, the Planck scale here, and you get cosmic acceleration. This is known as the DGP model. Unfortunately, it has ghosts, but it shows that you can actually generate cosmic acceleration out of modified gravity, which is very interesting direction to take. The other thing I wanted to tell you is that the nature of dark energy can also be probed using the cosmic web, because the presence of a smooth dark energy component slows down the rate of assembly of cosmic structure. So if you see here, these are n-body simulations. This is a universe with a cosmological constant, and you see that structure becomes frozen out because dark energy is pushing structure away, right? Dark matter is pushing gravity in, dark energy is pushing it out. And so you find that, the same supercluster you are seeing today was there already at redshift 1. But if you had no dark energy at all, you had just dark matter, things would be evolving very, very rapidly. The reason for that is also seen in the perturbation equation, where the expansion rate acts as a friction or damping term. So, this is very interesting because in the future, so I'll skip this because I'm out of time, but really this is a very, very key signature because in modified gravity models, perturbations grow at different rates from those in cosmological constant. And finally, I come to another final remark, and that is that, you have so many dark energy models now, all right? And faced with the increasing proliferation of dark energy models, you can proceed in two ways: test each and every one of your favorite models against observations, or reconstruct the properties of dark energy in a model-independent manner. This is the approach that Shomak and I and our student Varun Sahni and Starobinsky took way back when we wrote this PRL paper. So very, and so, you say that, okay, the cosmological constant is the simplest model of dark energy. Let's, make a test that could falsify a lambda term, right? Some observational test, right? So you ask the question, is it lambda or is it something else, right? These are known as null tests. And one way of doing it is that you expand your expansion factor in a Taylor expansion and take the third quantity, right, R. This is a dimensionless quantity divided by AH cube. And remarkably, you find that R is 1 only in lambda CDM. Right? In all other dark energy models, R is not 1. You define a second quantity, S, which is just Q minus half, R minus 1. Q is just the deceleration parameter, and it's 0 only in lambda CDM. So therefore, you have a null diagnostic. These are known as the state finders. The 1 and 0 only for lambda CDM. Right? And this turned out to be when we wrote this, was just like, very simple paper we wrote, but it became quickly known that it's very powerful because lambda CDM is this fixed point. The universe never evolves from here, whereas normal matter models of dark energy move from here up to lambda, and the Shaplegian gas goes from above. So it provides there have been almost maybe 700-800, not 1,000 papers on this state finder. I'm embarrassed actually when I see the citation impact, because it's one of the simplest papers we wrote, And it's a very fine fingerprint of dark energy, right? So if you can actually get your observation sophisticated enough to determine triple dot A, you are in very good shape. And I hope, the experiments like dark energy survey, Euclid and all can test this. So I end. You should be happy. I'm ending.
So there's a bus for the
It'll break down on the way back also. So there are 7 open questions for the cosmology. Actually, on the way back, there'll be no rush, so it'll zoom through, right? So is dark energy a cosmological constant, or is it something else? There are 7 key open questions, right? Very important question, right? Second question, does general relativity need to be extended to explain cosmic acceleration? Do we need a modified theory of gravity, right? Is it over with Einstein's theory? Third question, the universe seems to accelerate twice, at early times during inflation and again at late times for dark energy. Remember that all the galaxies you see were formed in quantum fluctuations during inflation, right? Okay, so quantum fluctuation is very important. And inflation is nothing but a super acceleration of the universe. So did the universe go through 2 phases of acceleration? One at very early times, then it decelerated, and then again today, right? Are they related? Nature should be economical. There have been several hundred papers on this approach, known as quintessential inflation. Fourth question, why is the density in dark matter almost the same as the density in dark energy? Right? Is this a simple coincidence, or is there some kind of interconversion going on? We don't know. Are dark matter and dark energy related? Perhaps. In fact, I wrote a very nice paper with Anjan Sen, and then again with my student, but we showed that if you modify the normal Lagrangian to, something, to a non-canonical scalar field Lagrangian, then this quantity, the kinetic term, plays the role of dark matter, and V plays the role of dark energy. So that was actually a unified model of dark matter and dark energy. We were very excited by this. And the second thing goes back to my very first slide, is the universe homogeneous and isotropic on very large scales and can easily accommodate very large superclusters, right? I think this will be answered by Euclid and other experiments, right? And the last one is very important today. Can our cosmological model accommodate the very old galaxies being observed by JWST, right? The James Webb Space Telescope, because this is really surprising. The oldest known galaxy has been observed at a redshift of 13 when the universe was only 2% of its present age. And it's a very massive galaxy, right? And now a total of 717 galaxies at high redshifts have been discovered. How could so many galaxies have formed so soon after the Big Bang? So is this a challenge for standard cosmology? We don't know yet. Time will tell. Papers are being written even as I write this, and I'm thinking about this, right? It's a very deep question, right? Has JWST thrown open surprises? But big breakthroughs await us, and the square kilometer array is there, Euclid is there, LSST, so many beautiful experiments are either functional or will be functioning. So we hope that some of these answers to the questions will come, and theorists are also working actively. So I end with this beautiful quote from Einstein: the significant problems we have cannot be solved at the same level of thinking with which we created. This is a very deep quote, right? Coming from a very deep person. And this may tell us that we are working with the wrong paradigm, right? that our paradigm needs to be changed. Right? And perhaps this is also true for dark energy, maybe for dark matter, maybe even for inflation. We don't know. Thank you all very much. I took
Thank
exactly
you.
1 hour.
So the floor is open for questions now. Anyone have any questions? There.
Thank you. Thank you, Professor, for the talk. My name is Rahul.
Hi.
I'm from biology, so my question might be very naive.
No,
I have very limited information about this, but not so limited enthusiasm for space. So I have two questions. One is, so as we know that the dark matter and the normal matter, that they do not maintain spatial exclusivity, they can interact, or they can move through each other. Basically, dark matter can move through normal matter.
Yes.
And at places where collisions happen, you say that matters tend to slow down, but dark matter still continues to go. So does it mean that in an expanding universe, dark matter will just outreach regions of the normal matter, like it will expand farther than the normal matter will ever reach, because that's not getting affected? And the second question is, when two black holes collide to form a bigger one, during that collision process, what happens to their spatial consistency or composition and that event horizon beyond which you cannot escape it?
Yeah, thank you. I'll answer the second question first. As you get older, memory fades. So soon I'll say, what was that first question? But anyway, so you see, this is very important because long ago, Hawking and Penrose proved something called the no-hair theorem for black holes, right? That every black hole is characterized by only 3 quantities. It's remarkable. Its charge, its mass, and its angular momentum. Now, this is amazing because suppose I want to characterize you, right? I'll say you have this lovely green jacket, you have a t-shirt, you have a necklace, you have a beard. All of us are characterized by numerous numbers. But the black hole is the simplest object in the universe. It has only 3 numbers. And it's perfectly spherical, or it can be rotating also. So what happens when 2 black holes merge, for instance, these 2 massive black holes, that 3 times the solar mass is radiated in 2 gravity waves through the equation E is equal to mc squared. That's enormous. That means in a fraction of a second, more energy passes through you through gravity waves than emitted by the entire visible light in the universe. Right? That much of energy. So the two, suppose you have a 3 solar mass object and a 5 solar mass object. When they roll around, they won't form an 8 solar mass object. It will be size smaller than 8 because a lot of that energy has gone out, right? But what will happen is that this new black hole will be rippling around, like a droplet of water, It'll wobble around and then it'll steady itself into a spherical shape. So this is what happens, right? Now, your second question concerning dark matter is the following, that yes, dark matter is more puffed up than normal matter, right? Because, normal matter, you see what happens is that when the galaxy forms, it radiates a lot of light. That's why the galaxy is flat, right? But normal matter, when it collapses, it doesn't radiate anything. So it remains spherical. So the sphericity is part of what the galaxy looked like, 1 billion years back. It was spherical, right? But then due to angular momentum and heat transfer, radiative transfer, it became flat. So a flat thing is surrounded by this halo of dark matter. That's the picture. But gravity keeps the dark matter together. It won't let it fly out.
Am I audible? Yeah. So, hello, Professor. Nice talk. So, my question is regarding machos that you mentioned. And in the macho section, you talked about failed stars like Jupiter. So, is our Jupiter consist of dark matter? If yes, then how? And if no, then why not?
Yeah, thank you for both the questions were very interesting. Now, you see, the thing is that in principle, all that you want of dark matter is that it doesn't shine. Because you don't see shining coming from the halo, right? So in principle, it could be a Jupiter type object, but you need lots of them. So the question is, how do you create so many Jupiters without creating also a few stars? And that's why I found the Jupiter idea not very appealing. because that implies an initial mass function that is very steep, right? Very peaked around the Jupiter mass, right? So in principle, I mentioned it out of just democratic concerns, right? But I believe if it's a macho, then it's something else. It's not Jupiter. Right?
Isn't there already a limit from macro lensing?
I beg your pardon?
Limit on machos from macro lensing, etc.
Yeah, that's the limit that I showed. Yes. There's a strong limit, right? On micro lens.
Okay, before we take any other question, can I request all the Delhi participants to please proceed towards the bus because it is scheduled at 8:15. So I'm sorry we're running late, but Spandan, will you please guide them towards the bus? Thank you.
Maybe if they have one or two questions, we can take them.
Huh? I'm so sorry about that.
No. Can't they stay till the end of the lecture? Do they have to? Can't the bus wait for a few minutes?
I don't know how to hold the bus now.
If they've come all the way after all, maybe they have a few questions, right?
Okay, please hold the bus then. Okay.
All of you come back.
Come back, please.
You should feed the driver a couple of samosas. He's happy. Badi baat kya hai?
So, please go ahead.
Yeah. It's on. Speaks.
Oh, okay. I just had two doubts.
Yeah.
One is, in one of the slides, you mentioned that baryonic matter will not be able to form those cluster structures, and the dark matter should be there for them to form.
Yeah.
So, is it the time scale that limits baryons from forming those structures, or is it the magnitude of the structures that limit it?
You see, the trouble here is that see, the CMB was formed at redshifts of 1100, right? Redshift is 1 plus z is equal to A naught over A of t, right? A of t is the radius of the universe, right? This is the universe, this is the A of t, right? Okay. So the CMB was formed somewhere here. Now, density perturbations, can you see the black whiteboard? You can see, right? So density perturbations, delta rho by rho, which is just rho minus rho bar over rho bar, right? This is the mean density. They grow proportional to A of t, right? In a flat universe. So if you start from delta rho of rho initial of 10 to the power minus 5, and you multiply it by 1000, you will get delta rho or rho now, today, now, of 0.01. But you want this quantity to be much greater than unity. In galaxies, it's 100,000. So there's no way you can start, because baryons coupled to CMB. That's the key thing, right? Baryons are coupled to the photons at that time, right? Because they are charged matter, right? The plasma is oscillating. So the amplitude of fluctuations in baryons is the same as in the photons. It just does not have enough time to grow. But dark matter doesn't care for photons. So it can begin growing much earlier. That's the thing.
Just one more doubt.
Yes,
in one of the simulations that you showed, that when two galaxies were colliding with each other,
yeah,
the baryonic matter were like rippling each other apart.
Yeah.
But the dark matter just went through each other.
Yes,
like, why didn't the dark matter collide with themselves? Like, am I understanding something wrong?
You see, that's a thing with dark matter. It is collisionless. It appears to be collisionless, right? Because if it was collisional, then it would not form the halo of the galaxy, right? It would collide with itself, lose energy, and fall into the galaxy, right? But it's a halo; it's all spread out, right? So it appears not to interact with itself, right? Or if it's interacting, it's very weakly interacting.
Thank you.
Professor, I was wondering what your views are on cyclic cosmology.
Cyclic cosmology. I love cyclic cosmology. I've written 3 papers on cyclic cosmology. You know, cyclic cosmology is a very beautiful idea, and you can realize it very easily if you just change the Einstein equations in this manner, right? So your A dot by A squared, are you acquainted with relativity? No? Sort of, little bit. But you recognize this equation? This is rho. Beautiful, beautiful, beautiful. So if you add to this, so there's an 8 pi g out here, which I'm missing, right? If you add to this a minus rho square by some constant term, you cannot go to large values of rho, right? If you go to, rho has to be limited beyond lambda, right? Otherwise, a square term turns negative. So what this means is that at rho equal to rho lambda, the universe will encounter a bounce. This is A of t. This is expanding universe, A dot positive. This is A dot negative. The bounce happens here. So these kind of models are there in loop quantum cosmology. And I constructed one with my Ukrainian collaborator based on extra dimensions. And so you don't have the singularity at all. Boom, the universe contracts and expands, right? And then if you have a positive, a curvature term like minus k by a squared, so the universe is closed. This is the cosmology Einstein favored. Then at late times, this can cause the universe to contract. So then you will have exactly what you want, a cyclic cosmology, which goes like that. I like this picture because it allows the universe to rejuvenate itself. You see, if you have a cosmological constant, right, which is my worry, is that, you know, it'll dominate everything because it remains constant, everything else dies out. So if I live 100 billion years from now, the stars would have died, everything would have died, only black holes would have remained, right? And you wouldn't see, that would be the end of astronomy and the end of life, right? So we would be living in a really dull, boring, desolate place, right? You know, you couldn't even read a book at that time, right? So I believe if there is dark energy, it has to be some kind of a transient phase, right? You know, that it comes and it goes, but what it is, I don't know.
Thanks, Professor, for this nice talk.
Thank you.
So in that slide where you were showing the primordial black hole formation, the oscillating candidate for the dark matter, so you need a bump in the potential to create the peak in the power spectrum, right?
Yes.
So what is the physical source? Is there any physical reason for such a bump in the potential? I mean, because usually people put it by hand, like consider a toy model, isn't it?
Well, you know, the thing is that we are not very sure where the inflaton potential comes from. We don't know, right? So our idea here was that just to show that, look, if you have it was a phenomenological model, right? That if you have a potential that is not completely smooth but has a bump, then you generically get primordial black holes, right? Now, how you achieve it, whether there is a phase transition or the inflaton field is more complex than we think, we really don't know. But but this is nothing to do with the oscillating scalar field. These are two different questions you are asking. So the oscillating scalar field is, I was talking about in connection with dark matter.
So, so about,
you can just shout, I'll hear you.
So, slide on where you were showing the oscillating field.
Yeah. No. You see, actually, I was a bit lazy, and I grabbed that picture from the internet. You know, because both inflation and you know, inflation has a scalar. So you are absolutely right. Thank you. You're very observant. Thank you very much. You know, we all need people like you in the audience, right? I thought people would miss it, but they didn't, right? So in inflation, what is happening is very interesting. This is phi, and this is the potential, right? So this is V, and the scalar field is rolling down. Now it encounters quantum fluctuations, actually. So it encounters fluctuations like, you know, pi square, and it's related to h cube over, I think it's a 4 pi square times delta t. T is the start of inflation, right? And so you see that this field is actually not smoothly rolling down, right? But it is encountering oscillations here, not fluctuations. You have to solve the Langevin equation, right? And in certain regions of space, what can happen is that the field can roll up because of this fluctuation. This is the RMS value of the field, right? And it can also roll down. So where it rolls down, you get our universe. But where it rolls up, you get an eternally inflating universe. This is actually Linde's scenario. So in fact, the universe has a very beautiful fractal structure. Most of it is inflating, right? So the universe, we are surrounded by, we are over here and we are surrounded by regions of eternal inflation, but the field never came down. Right? So this is eternal inflation. I think this is a generic prediction for all inflationary models because of the presence of quantum fluctuations. Yes. Yes, yes, but in different region of space. It's a stochastic process, right? So different regions are not causally correlated. So here it's a quantum fluctuation. So basically the field wants to go down because of the potential, but if the fluctuation is large, in some regions it can go up. But since the expansion factor is exponential, right? A goes like e to the power ht, regions with h is large where they go up win in phase space. Right? They get larger and larger and our universe gets smaller. Yeah, yeah, please go ahead. No, say that louder again, please. Sorry. Maybe the black hole will feel hungry. Maybe it likes you, more food. No, actually it is interesting because you see, in 1905, there was you may not have heard of this or you may have, there was a Tunguska meteorite, Tunguska explosion in Siberia, which demolished huge amount, 100 square miles of pine forest. And they never found a crater. So they always, even at that time, they said there's a primordial black hole that came through and the shock wave destroyed all the trees around it, right? And this has never been resolved. So I asked actually quite a deep question, and I myself don't know the answer because the Tunguska meteorite was certainly, if it was a black hole, it was very small. Right? That's it.
Professor, I recently read in an article about some new study from this year itself linking black holes and dark energy, saying that black holes might be a source of dark energy. Do you know anything further about that?
No, I don't know anything.
It's from February 2023.
I'm afraid I'm not aware of this work. Black holes cannot be dark energy on their own. I'll have to read this paper. I'm sorry, I can't comment.
So my question comes to what they only asked. So black holes as a source of dark matter. So won't you imagine some side, like in the galaxy collision, won't you imagine some kind of collisions of these black holes and produce some gravitational waves?
No, that's exactly what we are seeing, right? We are seeing black holes merging into larger black holes and we're seeing gravity waves, right?
Yeah, but doesn't that say that dark matter is interacting?
No, you see, the point is, okay, so that's an important question. There was a transparency here. I don't want to go back into it, right? Maybe, can I just go back to that transparency? It stopped. Yeah. This one, right? So you see here, these are the bounds on what can be dark matter. Oh, this thing has come here for some reason. Just killed my slide. Yeah, it's good. Thank you. Can somebody switch off these lights? Yeah, thank you. This one, these ones, yeah. These ones, yeah. So you see, now, the fraction here is the fraction of primordial black holes or black holes contributing to dark matter. And there are all these bounds here, okay? So the gravity waves that you are seeing provide bounds here. So if you have a solar mass black hole, right, or tens of solar mass black holes, you cannot have more than a few percent of dark matter to be in black holes, right? This is the bound. And you can ask me, where did I get this bound? The bound is very interesting because you see, if I have a very large black hole, or many of them, in fact, to have dark matter, you need many of them, then they'll disrupt binary stars. So there are all these wide binary stars, and you have very many of these black holes. They'll just disrupt the orbits of these black binary stars. If I go to still larger black holes, which are called supermassive black holes, then they'll disrupt globular clusters. They'll go and sit inside a globular cluster and start eating the stars belonging to this globular cluster, right? So we know that globular clusters are stable, and we know that there are many binary stars out there. So we can put these limits out here. And the final limit, of course, is from the CMB, right? So, and these are limits for microlensing. So there are a lot of different astrophysics has gone into making these limits. And that's why the only possibility for all of dark matter is tiny, right? Very, very tiny size. Did that answer your question? Huh? Thank
you. Thank you, Professor, for this lecture. My question is that how the concept of dark energy can help us to resolve or can help us to give an answer on the ultimate fate of the universe, the concepts such as big freeze or big crunch.
Yeah. Now this is stopped. How do I go down? The laptop is. Next, I want to scroll to the end of the talk. Okay, cool, I'll do that. So here it is. You see, this quantity stays constant, whereas rho decreases. So in the future, you have lambda dominating and the universe expands exponentially. So the universe expands forever, and the future of the universe is very boring, since this is what I said already, after about 100 billion years, all the sources of energy fueling stars would end, stars would die, and the universe would be left with planets, moons, and stellar remnants such as dwarfs, black holes, and white dwarfs. So eventually, black holes would evaporate, emitting Hawking radiation, and you would be left with nothing, only planets and white dwarfs, right? So this is the future of the universe, and unless you don't have a cosmological constant, instead of lambda, you have something that decays with time, right? Just like dark matter, right? And this comes back to your cyclic cosmology. We knew, it would be much more interesting if the current acceleration was to end. And when we studied cosmology, I'm sure as you have with Vaidya-Raychaudhuri, you know that a universe, normal universe, can either expand forever or contract, right? So I would much rather prefer something like this, because then you can rejuvenate the universe, and you can have many universes after hours, right? But it's an open question.
Hello,
Okay. Yeah.
Professor. I had a question.
Yeah.
Is the bullet cluster the only evidence we have for non-baryonic dark matter, or are there other observations that also suggest it is collisionless?
Would you like to comment, Shomak?
There are quite a lot of bullet clusters, right? So that is one. Bullet cluster is not only what is the cluster. Now there are about
now there are maybe 7-8 such systems where this kind of thing has been. So, but that's not the only thing, because the collisionless part of it also comes from the fact that there are no dark stars, dark matter stars, right? So it's just showing that the dark matter particles don't clump. Otherwise, they would have naturally formed clumped things. And in general, the dark matter distribution follows the mass distribution. And so there are no big dark galaxies or dark stars. That I think is the biggest evidence against it.
Any further question? So if not, let's thank our speaker. Yes, so I just want to thank all the Delhi participants for coming all the way up to here and listening to this great talk. I know it's a bit delayed, and Spandan will guide you towards the bus. He has the number of the bus driver, so he can take you there. Thank you for coming.
Thank you very much.
And also, I'd like to say a few vote of thanks. First of all, I'd like to thank our Honorable Vice Chancellor Shomogda for enormously supporting us to hold this event. And without his help, we could not have done anything. And then a big thank to our HOD, Professor Dipankar. Dipankar, and he has supported me a lot. Without his support, and I have consulted almost every day with him how to conduct this event and all, and he had patiently listened to all my queries and had given his views. Then I would also like to thank Professor Kandaswamy, Professor Vikram Fukun for there when we write the proposal to host this event here, and they were very supportive. I also like to thank our departmental manager Shivani and our lab superintendent Sudarshana Banerjee. They also helped a lot in organizing this event. And also, I'd like to thank our media team who helped me a lot in doing the publicity for this event so that so many people turned up ultimately. And also our IT team who helped with this live streaming and all. So with this, I would like to conclude this event. Thank you again for coming and joining for this event.
Stop the work. Thank you.